We are diving into our next chapter, chapter 12. That's probably our most intense chapter that is coming here. There is a lot of content that is in this chapter, so you're going to want to stay on top of it. That means that you really need to be reading along in the book. I know many of you are like, whatever, I get it from class, I'll kind of skim the pages. But you're really going to want to pay attention in the book and keep up on your active assignments, try practices where you can, because there's a lot of stuff that looks similar but is actually different. So make sure you are working on that. So you're going to start by doing the vocabulary for chapter 12. That is due Sunday night. We're going to get through hopefully sections 1 and 2 in class today, and then spend some time on section 3 on Monday. So make sure you read those sections over the weekend. All right. So chapter 12 is about kinetics. After this, we're going to be talking about equilibrium. So they're closely related to one another, but we've mentioned equilibrium throughout the semester as processes that are going in the same time in both directions. Technically, they're going at the same time at the same rate. And so kinetics is all about the rates of the reactions. And that's kind of the connection between. We have here pictured several different kinds of reactions, and they all go at different rates. So we have, an explosion of some kind that can be just a few seconds. And then we can have rotting food that might take a few days, ripening food and take a few days, rotting food might take a few weeks, months or years for our rusting, and then, aging from a baby to an adult can take a lifetime. Of course, this is more than one chemical reaction. This is more than one chemical reaction. Those things are kind of mixed together. I can't tell. Do you need me to turn out the front light? Yeah, okay. All right, so what we're looking at is how can we measure how fast these reactions are going? So what typically will happen in a chemical reaction is we'll start off with all reactants. And so we have the lighter colored kind of pinkish molecules at time 0. That's our reactant. And as time passes, we start to develop some products. And then more time passes and we have more products. But we get to a point where the amount of products that we're making in any given time frame is slowing down. So if we look in this first segment here, half of these change to our products, the light green ones. And then in that next time segment of equal magnitude, we didn't finish. We only did maybe half of what was left. And then we did half of what was left. So that means our rate isn't constant. Our rate is changing over time. And typically the rate will slow down over time. How fast it goes is going to depend on a few things. The main ones we are going to concern ourselves with are temperature and concentration. So we'll get to temperature towards the end of the chapter. The first part of the chapter is really going to be a lot about the concentration, particularly of the reactants. Some other things that might matter might be the physical state. So if we think about two solids sitting next to each other, they don't mix very well. So two solids might take longer to react with one another. Whereas if I have gases that can mix very easily or a solution, then those reactants can react more rapidly. So the physical state is going to matter. And then within that physical state, we have surface area. So that's connection to it. So if I have two solids that are one solid block and one solid block right up against each other, they're only touching in a few places. But if I have them ground down to powders and mix those powders together, on a microscopic level, they're still pretty big chunks, but there's a lot more interaction. So surface area plays a part too. We're not going to talk a whole lot about physical state or surface area, but that is something to keep in mind, is that you can affect the rate of something by changing the surface area. Okay, so why do these things matter? The basic idea behind how fast a reaction goes is that in order to react, the molecules have to collide with one another. They have to bump up against one another. So we have an example reaction here of ozone with nitrogen monoxide making oxygen and nitrogen dioxide. So in order to have this reaction, they have to hit one another, but they have to do it with two things. Enough energy for that reaction to happen. So if they just sort of lightly tap each other and walk away, they're not going to break the bonds within their own molecules in order to be able to move the oxygen from one molecule to the other. And they also have to be facing the right way. So if we attack the nitrogen monoxide with the ozone on the oxygen side, that's not going to produce the product that we want. So we have ineffective collisions, both because the molecules aren't oriented the right way and because we have the not enough energy. So these are pretty small molecules, pretty simple molecules. If you think of more complex molecules like biological molecules, you can have dozens to hundreds of atoms with only one specific place being the right place to hit that molecule. That's really going to slow down that reaction. And that's why we need enzymes to speed up those reactions, because the kinds of chemical reactions that cause us to live would take centuries to happen on their own if we didn't have enzymes helping them along. Okay, so what do higher temperatures do? Higher temperatures mean we have more collisions. So first of all, more chances for them to be facing the right way, but it also means that those collisions have more energy. And so we're more likely to have enough energy to break the old bonds and be able to form the new bonds. Similarly, higher concentrations are also going to provide for more collisions. So those collisions won't be more energetic, but we have more opportunities for the molecules to hit the right way. And then finally, with physical state, if they're in the same state, like if they're both gases or if they're both in the same solution, then they mix better and therefore collide more often. Or as I said, if there's more surface area between smaller particles, then there's a better opportunity for them to collide. Okay, so this is all about reaction rates. What we want to be able to do is to quantify or to measure how fast something is going. So when we're traveling at a distance, we think about the distance we have traveled over time. But in a chemical reaction, what we're going to look at is how the concentration has changed over time. So we can measure a couple of things. We can measure the product that is appearing, right? And so we can measure how that concentration is increasing over time, or we can look at how the reactant is disappearing and how that concentration is changing over time. Which one we measure really is a matter of convenience, because it's not like we can just stare at a bottle and know exactly what the concentration of something is. So we need to have a method to quickly and reliably get that concentration. Some chemicals that's pretty easy to do, others it's more difficult. All right, so mathematically what we look at is the rate is proportional to the change in product over the change in time. Now from here to the end of the semester, when we use these square brackets, that's going to mean the concentration specifically in molarity unless we tell you otherwise. Delta is change, and as we've done with other things, final minus initial. So within a given time span, at the end of that time span, what's the concentration minus at the beginning? What's that concentration? So for products, that is increasing. Reactants, it's decreasing, and so we get a negative number in here. So we use this negative sign to just make the rates always be positive. All right, so let's say we have this data here. What we could do is we could take measurements every few seconds. and, or in this case, it's every few hours, depending on how quickly or slowly the reaction's going. So maybe this is something medical and we're measuring somebody's blood for something, and we come in, you know, at 6 in the morning, and then we come in at noon, and then we come in at 6 at night. We do it every 6 hours. And so we take that measurement. Our reactant is going to go down over time. And so we look at, for any time frame, what is that change? So this is going down by negative 0.5. And then the time that it's passed is 6 hours. And then we just divide 0.5 by 6, and then use that negative because it's a reactant to make the final answer positive. Okay. So that's kind of how that would work. So we are looking at the average over a short period. So it's helpful not to do like the entire reaction as your quote unquote short period, unless you just have a super fast reaction. But this might be seconds, it might be minutes, hours, years, depending on what you are looking at. So if we were looking at the rusting of a nail, we wouldn't find a lot of change between 6 in the morning and noon. We might have to come in and measure the change from today versus a month from now, and do it once a month and see how much is rusted. All right, so we like graphs. We can plot this data on a graph. And what you'll notice is that this is a curve here. So for this reaction, C2H4, that's ethylene, and ozone, this is going down, and then the oxygen is rising at the same rate. And this is because they have the same coefficient. Both have the coefficient of what? We're going to look at something that's a little different in a minute. But the important thing here is that it's not a straight line. A straight line would mean the change was constant. So when you're looking at a graph, whether it's straight or not, or how slanted it is, we call that the slope. And the slope is what it's telling us the rate. So when it's more vertical here at the beginning, that's a fast rate. More vertical slopes are faster. And as it slows down, it kind of bottoms out. Okay. And then, of course, obviously, as the reactant decreases, the product increases. Okay, so I mentioned which one we're measuring really kind of depends on the chemical. So here are some ways that we might try and find the concentrations. If we have something that involves an acid or a base, it's pretty easy to stick in a pH probe, and we can monitor that. Only takes a couple of seconds for the probe to catch up with what the pH is. So pretty quickly we can measure changes in pH. If we have something that is colored, whether the product is highly colored and the reactant is colorless, or vice versa, we can measure that change in color. So we can use spectroscopy or colorimetry. Spectroscopy kind of covers a wide range from light we can see to light we can't see. Colorimetry specifically looks at the visual. So in lab in a couple of weeks, you should be doing a reaction with crystal violet. So as the name would imply, we have a purple reactant, and then over time that color gets lighter and lighter. And so you're going to measure not the concentration, but how the color changes. Well, how does that relate to concentration? Remember when you did your copper lab earlier in the semester and you looked at the spectrometer of that, as you change the concentration, you change the amount of light that is absorbed. And that is a linear relationship. So this is what's called using a proxy. We're not directly measuring the concentration. We're using the color as a proxy for the concentration. If we have a volatile substance or a gaseous substance, we can do gas chromatography. The problem with gas chromatography is that's going to take a few minutes to do. So this only works really well if we have a pretty slow process that it doesn't matter if it's going to take 15, 20 minutes to run a sample. If I have something that the entire reaction is going to be done in 15 or 20 minutes, it's not going to be really helpful to do the gas chromatography. And again, if we have something that the change is pretty slow, you can do a titration. So you've done titrations before in lab. Later this semester, you'll do some more acid-base titrations, but we can also do ones for things that are not acids and bases. If you take analytical chemistry, you can use EDTA to measure concentrations of things like calcium. And calcium is something that in solution is colorless, but when you use EDTA with an indicator, then it will change between a pink color and a very dark blue color. So you can use titration for some of those things. So the disadvantage of some of these processes is that they're slow. Okay. So now let's look at some data. And I think this is the same reaction that is on the graph that I gave you. Okay, so we might go through and collect the concentration of, in this case, we're looking at ozone. So is ozone a reactant or a product here? Yeah. It's a reactant, so we expect the concentration to go down, right? Okay, so graphically, this is going to start high and go lower. So on the graph that I handed you, you should see that. And just like we saw on the others, it's kind of curving as we do that. Now, from this data, I can't really just eyeball this and know that it's faster at the beginning than it is at the end. So the advantage of a graph is that it's immediately obvious that it's more vertical at the beginning and it is more horizontal at the end. So that's one of the advantages of putting it into a graph form. All right, so this is the same data, it's just condensed to a smaller form. Let's say we wanted to find the rate. How are we going to find the rate? What is the rate of this reaction? Well, we could have the rate overall, and that would be going from the end. So here's the 1.10 final minus the initial 3.20. And times 10 to the minus 5, because they're both times 10 to the minus 5, and divide by the total amount of time that's passed. Okay, so that would be the overall average. All right, so on your graph, the line labeled B is this calculation. So if you're writing down this calculation, you might put a B next to it so you can correspond to that. So that can kind of tell us big picture one reaction to another, but it doesn't really show us that it is changing overall, right? So we might want to know, well, how fast is it going at the beginning? So we might look at the first 10 seconds. Okay, so before I do that, we've got to see the answer to this. The answer to this is 3.5 times 10 to the negative 7 molarity per second. So now let's try and get something that's closer to the beginning. So the beginning, the first 10 seconds, instead of using the 1.1, I'm going to use the 2.24 as my final. Okay, so this is my time frame, and at the end of that time frame, this is the final. Now, am I going to divide by 60 seconds? I'm only going to divide by 10 because in this time frame, only 10 seconds has passed. Now, if I look at these two numbers, 7.8 compared to 3.5, this rate in the first 10 seconds is more than double that average rate overall. Okay, so the total average isn't really a helpful number, but having that first 10 seconds, that really kind of gives us an idea of, okay, how fast is this going at the beginning? And then if I want to see how it changes over time, then I can kind of look at these last 10 seconds. And so I'm going to go back to using the 1.1, but I'm going to use 1.23. And then what time frame am I going to use here? Am I going to use 50 or 60 seconds? No, it's still 10 seconds that have passed from one to the next. Okay, so if I'm looking at that, we have this scenario, and we end up with a much smaller number, which is what we would expect because we know that it slows down at the end. Okay. So this top one we said was B, this one is C, and this one is E on your graph. Okay, so there's a couple of things that we want to think about with this graph. We want to think about how to best judge what's going on and what's going to be useful for future things, because what are we going to do with this information for the rate? We might want to be able to predict how things are going to change over time, and we might want to predict how the reaction proceeds based on one reactant versus another reactant. Okay, so this is just the graph that you have. What are the things that we looked at? We looked at the average rate over a period of time. And that's what each of those calculations. And so we have concentration 2 minus concentration 1 divided by time. Since it was a reactant, we had a negative in front of this. If it was a product we were looking at, we would not put the negative. Final answer is always positive. So we pointed out B, C, and E on the graph, but there are two other lines on the graph that are important. A is the D is the instantaneous rate. And this is the rate at a particular instant. So we've got a line that is coming right up against that curve, and it's only touching it at one point. We call that kind of a line. Let me remember. Looking back at algebra. I'm going to come back to the slide, but see how it just touches right in the middle here? This is what we call a tangent line. So I'm going to use that word throughout this chapter. The tangent line, not only is it only touching in one point, but its slope right here is the slope of the line right at that point. That if I were to look at how the slope was changing on the teeniest tiny level as I go through here, the slope right at that one point is the slope of the tangent line. Now, if I don't have a final minus an initial, how am I coming up with that slope? That's where calculus comes in. We're not going to do the calculus, but we're going to know the result of the calculus. The result of the calculus is we're going to come up with this slope at this point. And that's what's really helpful to us to know what's going on. Okay. Now, A is also a tangent line, but it's tangent at the very beginning. And so that is the initial rate. So it is an instantaneous rate, but it's the instantaneous rate at the moments the reactants are mixed, the highest rate that we have. So we are going to be looking at what's called the rate law on Monday. And in order to determine the rate law, we compare initial rates. So we have to be able to figure out what initial rates are in order to determine the rate law. Now, I do sometimes on quizzes and tests offer a picture of a simple graph and have a line and say, what is this? Is this the initial rate? Is this an arbitrary instantaneous rate? Is it an average rate? So make sure that you know that terminology and how it compares to what you're looking at on the graph.